Okay, so I'm very happy to talk to you today about how to make graph convolutional neural networks work for reactions. Um, and there are several like projects and interests that I'm up to. Um, I'll today talk about the machine learning of reaction properties, but I've also got a lot of work of how to relate error to uncertainty in machine learning, how to use machine learning for retrosynthesis or for the design of enzymatic reactions and cascades, and a lot of work on how to make clean databases of enzymatic reactions. So if you're interested in any of those and they don't come up today, just feel free to email me. So today we're going to talk a little bit about how graph convolutional neural networks work for a molecule and how we can adapt them to also predict reaction properties. So that will be about maybe 15 minutes, 20 minutes, and then we'll dive into a hands-on tutorial where I'll teach you how to program these things literally from scratch. So we will use PyTorch and PyTorch geometric, and starting with that and a nearly empty file, we will actually program that. Like to a fully usable model that you can use in your research if you'd like to. I'll type it all out, but there's also a solved exercise notebook just in case you want to copy paste stuff. So when we talk about property prediction for molecules, and reactions for molecules, we have a very large set of options that we can use. For example, we can use a string to represent a molecule and then put a transformer on top. And last week there was a very exciting talk on this. You can also use a fingerprint where you would try to expertly design a few properties that may match your molecule to your target. You can use graphs, you can use coordinates. The group I'm currently in works a lot with coordinates, but I'm more interested in the graph stuff. Now, for reactions, the list gets pretty short. There's some work on strings, and that works well for some cases. There's a lot of work on fingerprints, but usually they don't generalize that well. And there's some work on using two graphs, so one for the reactants and one for the products in the reaction. And I'll only talk about graphs today, and I'll add a fourth option to this list of reactions, and I'll show you why it works better. So what's a graph convolutional neural net? So I think you all heard about convolutional neural nets for computer vision. And the way it works is you pass an image and there's a filter that looks at some of your pixels and it makes a new value out of those that are in there. For example, it could detect whether there is a horizontal line, so there's something that's very dark on the top and very light on the bottom, and that would be a horizontal eye. And then you could take those features and aggregate them and make your image smaller, and then you would again filter and aggregate and hopefully arrive at a vector of your image that is helpful to relate it to a target, for example, to detect a cat or a dog in a picture. And for molecules, we can do kind of the same. So we start with a molecule that, of course, like in reality is a three-dimensional object. And then we'll simplify it by using a graph instead. It's an undirected graph, so we have nodes, that these are the atoms, and we have edges, these are the bonds, and we can attach some features to the atoms and bonds, and then try to iteratively update that to get a representation of a molecule that is again a vector. So you see, it's kind of similar to the graph convolution, to the regular like image convolutions, in that we want to try to get a vector, and that then we can relate to target properties. So if we dissect a graph convolutional neural network a bit more, we start with a small string. We make a molecule out of that. We will use RDKit for that today. If you've already heard of it, that's great. If not, I'll try to teach you the basics. And we'll make our own graphs from that and then exchange information. So we do a few rounds of so-called message passing, which means that we'll update the states of those nodes and edges depending on the local environment. And when we're happy with our embeddings, we will sum them all up to get an embedding of the molecule, because in the end, we want to predict molecular targets like solubility or antibiotic activity, and then we pass that through a neural network to relate it to the target. And that's where most talks stop. And I find that utterly disappointing because just based on that superficial explanation, I don't really get what message passing is and why it's important and why it works. So this talk will not be like this, and we'll actually dive into the details. So imagine if you had this really simple molecule, just 3 atoms. It is connected by 2 bonds. So we have 3 atoms, 2 bonds. The first thing that we are going to do is split up the bonds in 2. So instead of having 2 bonds, we want to make 4 and make them directed. So we have a bond from 1 to 2 and one from 2 to 1. And the same for the other sides, 1 to 3 and 3 to 1. And I hope you see my cursor, because otherwise my explanations will be a little bit hard to follow. If you can't, let me know. So we make this list of bonds, and then we start with some initial vectors of these directed bonds that are made up of some embedding of the atom the bond originates from, which is a very simple encoding of atomic number, degree, charge, chirality, hydrogens, and so on. So it's super simple that we can easily infer from this molecular graph. And then we also attach a super simple representation of our bonds, which is basically bond type, whether it is conjugated or in a ring, and some stereo information. So we will concatenate this, and you already see here 1 to 2 is a little bit different than 2 to 1, because although the bond embedding, which is undirected, is different, is the same, the atoms are different. So once we have made that information, so this is really just concatenation, we will pass that through a single linear layer to get some hidden representations of each of those directed bonds. And then we will update them based on local information. And the reason, the way this works is that we look at each bond and see whether there is any incoming information in a directed sense. For example, if I look at the bond from 1 to 2, pointing in this direction, there is some incoming information from atom 3, because atom 3 is a neighbor of 1. So if we want to update this H12, we need to take into account H3 to 1. So everything that is incoming to 1, we will not take into account the reverse message, like 2 to 1, because that will just lead to an over smoothing of all of our embeddings. Now, if we look at 2 to 1, there is no incoming message. There is nothing attached to 2. So they will just be a vector of zeros. By the way, these ages are usually of size a few hundred to a few thousands. For 1 to 2, we have 1 incoming message. From 2 to 1, and there is no incoming message to this 3 to 1 bond. So this is all 0. So we will pass those incoming messages through a linear layer. And as you see here, we will take our initial embeddings that we had. So these are the H0s that we made in the first step. And we will add those processed messages that were processed through a linear layer of a neural network to get some updated representations of our edges. And we will repeat that a few times, usually like 3 to 5 times, to iteratively update our embeddings based on the local environment. So in the first step, for example, this bond 1, 2 would get information from atom 3 also. In the next step, it would also get information from everything that is attached to 3, and so on. And in the end, we want to aggregate this to atomic embeddings. So we will say atom 1 has 2 bonds. So we will aggregate that information that is coming in from 3 to 1 and from 2 to 1, and we'll concatenate this to the atomic feature that we had in the beginning. Same for atom 2 and 3, and then we pass that through another linear layer to make our atomic embeddings. So this is message passing, what we discussed now. And then you can either sum it up or average it to make a molecular vector, and then just pass it through a regular neural network. And that is a flavor of of message passing that was implemented by the group I worked in at MIT for 2 years. In 2019, I joined the group in 2020, and then added a lot of new functionalities to that code. So it is just 3 linear layers, and a little bit sophisticated way of how to see which information can update which bond. So this is already known. This is well used. A lot of papers actually use that one to make models for diverse molecular properties ranging from like solubilities to IR spectra, UV-Vis spectra, antibiotic activity. There's a really long list of what you can use that for. If you're interested, we just submitted a new paper. It's currently on ChemArchive, and there is a really long list that is not exhaustive of what you can do with that architecture. If you want to look that up, that is the paper ChemProp. Now, we wanted to talk about reactions, and this is only for molecules. And what the group I worked in previously did is to say, well, I've got a reactant graph, I've got a product graph. Why don't we just encode them separately, like do message passing on the reactants and then the products, and we somehow combine them? And what they did is exactly that. Message passing on the reactants, message passing on the products. You end up with some elaborate atomic features for both, and then you subtract them, and you need to track which atom is which. For example, your oxygen here is labeled 5 and 5 here, and then we subtract those two vectors from each other, and then we end up with reaction encoding. We can again sum it up, get some reaction representation, pass it through a neural network, get our target. That seemed to perform very well. It turned out later that it performed well due to data leakage to the test set. And when we tested it on new reactions, it performed very poorly. And the reason is that there's no interaction between the reactants and products, really, apart from that minus sign. And if you have, for example, reactions that are not unimolecular, so two reactants reacting with each other, they can't even exchange information. So reactant 1 will not see what reactant 2 is. And if you think about organic chemistry, if you, for example, have a nucleophile and an electrophile reacting with each other, they kind of need to know what the other one is doing so that you know which reaction happens. So what I instead tried to do is to follow a different route, namely instead of encoding reactants and products separately, you would encode the so-called condensed graph of reaction. And that is a graph transition state. It is purely artificial, so this is no mechanism, as you would know from organic chemistry textbooks, but it tells you that there was a bond, for example, between 3 or 4 here, and from 1 to 3, there was no bond in the reactants, but now there's a bond in the products, so it would encode all that information. So how this would look like technically is that instead of passing one molecule, you now pass a pair of 2. And they need to be atom maps, meaning that you need to track which atom is which, so we can correctly set up this condensed graph of reaction. And then our atom and bond features would have 2 labels, because we need one part that corresponds to the reactants, this is the gray part here, and one part that corresponds to the products, which is the red part here, because, for example, the degree or chirality or number of hydrogen bonds might change during the reaction. And the same for bonds. We have one part that corresponds to the reactants and one to the product. And the really cool thing about this is that it's super flexible, and we can even do unbalanced reactions, which the previous workflow wasn't supposed to do at all. So for example, if I had this very incomplete reaction, you see here atom 3 just vanishes and is gone from the products, and there's just a random atom 4 appearing, which might have been a solvent or so, or a reagent, a catalyst, we don't know. If you pass that through the previous workflow, it would fail, because you need to subtract the atom features from 3 in the reactants from 3 in the products, and there's no 3 in the products, so it would just segfold. Of course, you could introduce some bug fixing and just subtract a 0, but that also didn't work well in our case. But if you move to this condensed graph of reaction, you actually balance the reaction without doing anything, because you see that this reaction, this bond 1 to 3, it is there in your reactants. It is not there anymore in the products, but you still know that 3 must be there in the products. So you balance your reactions for 3 which is pretty cool. And it is super flexible because once we have that CGR, it just means that our list of bonds on atoms is different than from just the reactants, but the whole thing with message passing and how to aggregate that and how to pass that through the feed-forward neural network, it's all the same. So it's really just a different way of making our graphs that leads to a whole new possibility of using graph convolutional neural networks for reactions. So let's see how this performs. And I'll compare the results of this work to other graph convolutional neural networks. This is this dual encoding that I presented to you before. And there's a lot of fingerprinting work, as I already told you. So the reaction community loves to do fingerprints. There are some very elaborate ones, like bird fingerprint. This is actually based on a transformer. There are some that are expert made, and there are just some very simple ones like Morgan fingerprints, and you just subtract the two or concatenate them. And if you compare that, for example, for a set of computational barrier heights of about 12,000 reactions, and then we can also reverse them to make a little bit more data, you see that our CGR approach outperforms all the other ones by a really large margin, and it doesn't really matter whether you hyperparameter optimize this CGR approach or not. Of course, it gets a little bit better, but even the default very, very tiny model size outperforms all the others, which have about 10 or 20 times the number of parameters. Pretty cool. We can also use that for reaction rates. So these are computation reaction rates, and again, the CGR approach really outperforms all of the others. And there are a few more test systems that we did that you can find in our paper. And you can, for example, also apply these to region selectivity. So I already talked about barrier heights and rates, and there are two cool publications you can check out. You can also use that to try to predict what outcome you will have of reaction. So if you have a region selective reaction and the reaction might happen in one part of the molecule or another, you could score them both with the CGR algorithm and then see what the model thinks is more likely. There's also some work by a colleague of mine on kinetic solvent effects on reaction rates. And there you would use the CGR approach and pair it with another neural network for the solvent. So with that, I'm done with my presentation part, and I'm really excited to go to the hands-on part because that's I think where all the meat of this presentation is. So if you follow me on github.com /reaction workshop, or you use this link, it will take you to GitHub. And while I go there, I'll maybe give you a quick break for questions. So if you have a question right now, you can just pose it to the chat and I'll monitor the chat a little bit. I already see there is one from Greg. Is it representing a real transition state? Well, for some reactions, the CGR is the real transition state. For some, it is not. It is the real transition state if it's an elementary reaction, and it is not if the reaction is actually consisting of multiple steps, multiple elementary steps. I hope that answers your question. And then I see another one from Anna. If you feed the model artificial transition states not necessarily occurring in the mechanism, how well does the model generalize to reactions not in the training set? Yeah, that's an excellent question, because that old model that we had with those dual embeddings, it wouldn't generalize to new reactions at all. And the CGR actually does to some extent. So if the transition that you're looking at is somewhat similar to something that it has seen in the training set, it will probably give you a rather good prediction of the activation energy or rate. So like to date, this is the model that generalizes best. That's not to say that it generalizes very well for everything, because of course, neural networks are in general not very good at generalizing beyond their training set if it gets too far away from what it has seen. However, what I will show you in the hands-on part is that there are a lot of works that only train on one type of reactions. For example, you only have nucleophilic substitution, SN2 reactions, and then you have 1,000 of these SN2 reactions with different substituents in the reactive center. And then you can even train a one-hot encoding of those different sites, like those sites connected to the reactive center, and you can get away with it. You can get really good performances for that. Can it generalize? No. Do you have any slightly different substituent than what is in a training set? You can't even process the thing, let alone make a prediction. And that's something that's very cool about this message passing on the condensed graph of reaction, is that it can generalize a little, and it tries to understand the chemistry that's in a reaction. And it can also exchange information between the different reactants, which of course is a very important part of chemical reactions, is interaction between the different edicts. I hope that answers your question. Also, it was a very long answer. Okay, there's another one. How do you generate the gas for the TS? Okay, so the graph convolutions I speak about today, they are purely 2D, which means that we only work on the graphs and we don't work on the three-dimensional aspects of it. If you're interested in three-dimensional stuff, I can send you a really good paper after the talk from a colleague of mine. But currently I'm only working on 2D. So the initial guess is really an interpolation between initial and final state. Speaking of graphs, so you start with your reactant graphs without any 3D coordinates, and you end with a product graph without any 3D coordinates. And if there's a bond in one and not the other, you would just attach that to your CGR. And if the bond is the same in both reactants and products, it will have the same labels for both. And if it changes, for example, it's 0 in one and 1 in the other because the bond is forming, you would also see that in your feature vector. Any more questions? Okay, there's another one. How about chirality? That's a very good question. So what I'm presenting to you today is there are some chiral tags in the features that we use, but it's not very good at enantioselective reactions, and that's actually an open question in literature that I'm trying to address with my current work, but it's still a little secret yet, so I can't tell you too much because this will be recorded in public. But if you shoot me an email, I'll happy to talk more about it. Okay, I think there are no more questions, but if there are, feel free to send them to me. And if you have clicked now to GitHub, you can see there's workshop exercise and workshop solution. And I want you to click on workshop exercise and click on the Open in Colab button. And as I said, I'll do an awful lot of typing, and I'm a fast typer. So if you're not, or if you like on a tablet or on a phone, you might just want to copy paste a little bit and not type it all out. So if at any point you don't want to type anymore, you just go to the workshop solution notebook and you can just copy paste everything that I'm going to type. But it will be more fun if you follow along. Okay, and then Alvaro's also asking all the fragments should have covalent bonds, right? So what I'm showing you today is only about covalent bonds, but it is rather easy to generalize to other like interactions too, but we'll not do that today. Okay, and we can already run the installation part. I'll just run this anywhere. You can also read, of course, through it and make sure that I don't spy on your data. And we'll install some basic dependencies like rdkit, numpy, scikit-learn, and pytorch. We'll also install chemprop, that's the message passing neural network that I talked about before, and we'll use it a little bit in the end to give you an out-of-the-box model that works if you don't want to program anything on your own. And then this is all based on Torch geometric, so we'll have to do some installation of Torch. And as you see here, I'm installing the CPU version of Torch. If you install GPU version, it will be faster. But the models are really efficient. So we will train on a real data set today. No cheating. I didn't pre-train this on anything. You will not load a pre-trained model and then add like one more epoch. We will really train it from scratch in like a minute or so on a real data set that people use in the literature, and you'll get good performances. But of course, if you do this on your own cluster, you might want to install the GPU version. So that installed, and we're loading a lot of dependencies. And then I made one single cell that I pre-typed, because this is just making atom features and bond features on RDKit atoms. And I'll show you in a second what that does. This you can exchange to any featureization of atoms and bonds that you like. And this is why I don't code it out with you together, because it's pretty boring. So the fun stuff starts now. So you see, I made already a function that makes a molecule. And what it does is it uses RDKit to make a molecule from smells, and all the other stuff that's in that function just prevents that hydrogens are removed when we specified them. So let's try it. We will make a molecule, for example, CCO, it doesn't really matter. And ChewPython is pretty cool. You can actually see the RDKit molecule, so you can get a notion of how these looks like. And if you ever worked with RDKit before, you probably know that you can that molecules are made of atoms, and you can get them with molecule.getAtoms. And we can just iterate through them and print our atom features, and we'll pass this to see what the featureization that I predefined above here does. And we see there's a one-hot encoding of the atom symbol, of the degree, of the formal charge, the total number of hydrogens, and the hybridization. And if you think back, also aromaticity and the mass, if you think back on the slides, that's just exactly what I was telling you here. The vector length is a little bit less because I didn't include every element in the periodic symbol system, so that it just gets a little bit easier to read. So we have 3 atoms in our molecule. The first one is a carbon, the second one is a carbon, the third one is an oxygen, and we see that in that one hot encoding of the elements. Then we, for example, see the mass here and the formal charge and so on, which is 0. And we can, of course, do the same for the bonds in RDKit. If you say get bonds, we get all the bonds, and we can, of course, iterate through them. So we have our bond features, B, and we see we have 2 bonds, and there are some values that are basically, am I a bond? Am I a single, double, triple, or aromatic bond? Am I conjugated? Am I in a ring? So these are all single bonds, not in a ring, not conjugated, not aromatic, not anything. And just to make sure that we implemented that hydrogen thing right, that just means that if we had hydrogens in our initial molecule string, that they wouldn't be taken away. So I can make water with this command, and then I would have explicit hydrogens, or I can just make water with implicit hydrogens, and the hydrogens would be attached to that atom here. What you choose depends on the data set. For reactions, it very often makes sense to include the hydrogens if they are important to your reaction, if the hydrogens change, and if you have them mapped, because every atom that we have here needs to be mapped in a reaction. So if you have mapped I hydrogens, you should definitely make use of that information. If you don't, then you'll just use the implicit hydrogen option. Now, the next thing that we need to do is, now that we can turn smells into an RDKit molecule, is to make a graph. We already know how to make those initial features, and we'll use that now to make our own graph class. So we'll design we'll define our class molgraph. And upon initialization, we want to pass it small string because that's what's the input, and as output we want to have our graph. So we will assign self smalls to smalls, and then we'll make empty lists for the features of all atoms, for the features of all bonds, and for all our edge indices. So saying which bond, which atom is connected to which. And we'll start by making our molecule with what we already defined, make molecule. And we should also count how many atoms we have, and in RDKit, that's get num atoms. So now we can iterate through all of our atoms. So we'll go through each atom, and our atomic feature vector will just be atom features of this atom, which we need to retrieve from the molecule with the help of RDKit, get atom with index. And then we can append that to our list of feature vectors. So this will just be a list of lists. The reason why we write this is that we later want to generalize this to reactions, and this will be very helpful to us. Of course, for now, we could also write this a bit quicker with a list comprehension. Also, for all of you working with vectorized stuff, I'm very sorry, this is a list. You can also make it a vector and vectorize over it. But for today, I think this is easy for everyone to follow and sufficiently accurate for what we want to do, sufficiently fast. RDKit has a function get bond between atoms that we can use to get all the atoms that are going from this atom that we currently selected to the second one. And well, if we don't have a bond, we just continue. And if we do have a bond, we want to make bond features. We already set this up, and again, you can exchange that to anything you like. And we will append that to our list of features. And if you remember, we will make this directed bonds where the bond part is undirected. So this will be the same for 1 to 2, 2 to 1. It will be the same B1 vector. So we will append it twice. Once for the forward bond, once for the backward bond, and then we'll append this to our edge indices. So we have once the bond from A1 to A2, and then another one from A2 to A1. And then we are done. Okay, Murat is asking, how do you satisfy permutational symmetry? That is in the aggregation function. So after we do the message passing, we will sum up over all atoms. And then if you sum up, it doesn't matter whether atom 1 or atom 2 was first, because we just sum over all of them. So that's in the aggregation function. Okay, so our molgraph class is done. So let's test it. If we make a molgraph of the molecule we had before, we can, for example, just print everything to make sure it functions as intended. So we can iterate over the F atoms and just print the index and the feature vector. And we can also iterate over the edge indices, G edge index, GF bonds. And print our indices of all the atoms. And this is called bond features. So this was the first typo out of many. I'm very sorry. We will probably encounter more during this course. Now, what we see here is we have 3 atoms and then 2 bonds, and they look just right. So when you think back about the molecule, there's one from 1 to 2 and one from 1 to 0, and that all looks good. Okay. Also, I'm a little bit confused about the edge indices. I'm not sure if I made them right. No, it looks all good. Okie dokie. So when we look back into our graphs, okay, there's another question. Do you have double-typed self F bonds append? Yes, I did. And that was on purpose because we have that forward bond from A1 to A2, and then we have that backward one from A2 to A1. And then I actually see where I made the mistake and why I was confused. If you're typing along, you need self-index extend because not append. We want please, if you are typing along, change append to extend because you want to add both this bond and this bond to a list, and they both have the same feature vector because we are still at this stage where the feature vectors are undirected. So for the first bond, it is B1, and for the second bond, it's also B1, and that's why I doubly appended them here. Okay, I hope you corrected the extend arrow. That's very important because otherwise we'll run into problems later on. So now that we have our mol graph set up for one molecule, we of course want to train on a whole data set of molecules and not just one. So we need a class of for our data set, and we'll inherit that from dataset from PyTorch geometric, which we loaded up here. This is a data set that is not being held in memory, so we can make it as large as we want to, and all the graphs will be regenerated on the go. Of course, you can also cache this data or make a data set that fits into memory. Just for reasons of generality, if you want to use this for a very big data set, I'll not use the in-memory version today, but of course you can if you only work with small data sets. So whoops. Let's make our chem dataset. Now we want to pass it smiles, of course, our molecules and the labels, so the targets that we want to predict, and a mode that will for now be molecule, and later we will generalize this to reactions. And since we want to inherit all attributes and methods from this dataset class in PyTorch geometric, we also need to call super. If you're not very proficient with object-oriented programming, I'm sorry that I can't cover it today, so you'll just use this as a magic line. But I can recommend you good tutorials if you're confused. Okay, so the first thing that this chemical data set expects, if you look into the documentation of the PyTorch dataset class, is that it needs to that you need to set the length of the dataset, so how many data points are in there, and how to get one of them. So, well, the length is very simple. We just return the length of however many smiles we have in that dataset. And if we want to get one item, it again is very simple. We should pass a key that would just be an integer of the first smile, the second smiles, the second molecule, and so on. And we will return something that we will program now. Namely, we need to process that key and then return our data point. But of course, this is not set up yet, so we will do that next. If at any point I'm too fast or too slow, just let me know. So if we want to retrieve one data point, we need to first get it from our list of small strings. And we will now check that our mode is molecule. And in that case, we will make our mol graph with the mol graph class that we already programmed. And else we will just raise a value arrow because we didn't implement anything else yet. So we will make our molecular graph with the class that we already did. And then we need to transform this into a data point that PyTorch geometric understands. So we will, in a second, write another function that will transform our molecular graph to an actual data point. So we need a mol graph to data method. And now here's a little bit the meat of how to make it. So what we'll start with is we'll make a empty data point. That's also, if you look up the PyTorch geometric library, you will see that this will just give you an empty data point, and it expects different stuff to be set, namely data X, and we'll program this in a minute, data index, data attribute, and data Y. So the X is the feature vectors of all your nodes in your graph. Now that is easy because we already have that in our mol graph. So we'll do mol graph.f atoms, .f atoms. And now, since this is PyTorch and this is just a list, we also need to transform this to a torch tensor. So we need to call torch tensor on it. And we'll tell it what type to expect, namely a float. Because this will be our feature vectors of our atoms, similar to what this is. And since there's also some scaled masses here, we need a float, not an integer, although the rest of this is one-hot encoded. Then our edge indices, that's also something that we already know. We also need to make a tensor out of it. So we call molgraph.edgeIndex. And we also give it a type, which is an integer. And we need to do a little magic with our shapes that I won't go into detail today because we've still got a lot of programming to do. And our edge attributes, as the name suggests, are the attributes that we have, like the feature vectors that we have for our bonds. So like the atom features, we just pass that to a tensor. And this is, of course, also of type float. And our Ys are the labels, so the targets that we are trying to predict. So to get that, we again make a torch tensor. And we need to look at our labels and retrieve the right one. So if our key was, for example, 0, we need the 0th element of that array or that list. And this, of course, also is a float. We'll only do a regression today, no classification. So I just hard code this to float. If you want to use this in a other project for classification or for something that can do both, don't hard code this. Also, full disclaimer up ahead, I will hard code a lot of things today just to make it easy for you to follow along. And if you make this into your own code and publish this with a publication, you should really have some, like you should not hard code all this, but actually pass it as an argument. This is something data smells that PyTorch geometric doesn't necessarily need, but we'll just also set this because it will be convenient if you want to do some arrow shooting. So here is our finished chemical data set. And to make to load a data set from the internet or from a file that you have at hand, we also need to construct a data loader. So we'll do that next. We'll pass some path. We will tell it whether it needs to shuffle the data set, which is, of course, a good thing for training. We can specify the batch size and the molecules. You can also, like there's a really good documentation. If you look at PyTorch Geometric, it will tell you how to make good loaders. And I just copy pasted a little bit from there. And for us, we will use pandas to read a CSV file at data path. And now, don't hate me for this. We will just hard code the column that the smiles are in and the column that our targets are in. And please, if you do that in your own project, pass an argument, don't hard code this. But for the data that we use today, I know that smiles are always in the first column, so just type a 1 here. And I know that the labels are always at column 1. And we already set this to type float. I'll just use single precision because we don't need more today, but you can set that to whatever you like. Whoops, there's a dot too much. Okay, and then we'll make our dataset out of that with the chem dataset that we just programmed, which just needs a list of smiles and a list of labels and the mode that we want to use it in. And then we are done because we can pass that whole thing to data loader from PyTorch Geometric, which is very handy because it will do all the batching for us. It will make a super graph of all the different molecules with little graphs that are not connected to each other, and it will just put that into a single batch that will make it very efficient. You don't need to zero pad anything by hand or worry about the sizes of our graphs or how they are connected. PyTorch Geometric will do all of that for us. If you look into the documentation of the data loader class, you will see which arguments you need. I will make this serial, so no parallelization. I will pin it to memory. I will not use any sampler. If you want to learn more about these options, please just go to the documentation, PyTorch geometric.data.dataloader. And then we are done. Oh, we should probably also return our loader because otherwise we can't access it. And there's some comma missing here. Here we go. So let's see whether this works. I prepared some dummy data for you in this reaction workshop GitHub repository, which has different stuff, and we will use the ESOL stuff now. And if you just take a quick look how it looks like, the first column is mouse, as I hard-coded it in a very ugly manner. And the next one is the solubility, which we will try to predict in a second. And if I will now copy paste this and not type this out. If you go to github.com, HS reaction workshop, raw, main, data, ESOL, train full, this is just what I showed you. This will be in our loader. Pandas can actually load stuff from the internet without you downloading it, which is pretty cool. So we'll just use that. And I'll also copy paste some code to look at the data. And I made a MolGraph dataset, a typo here. 1p too much. And I also, because my English is terrible, I forgot that there is a U in contiguous. And here it is, our data set. You see that it batched up 50 molecules, so 50 smiles, and it has 65 atoms in that batch each. So we have 65 feature vectors for each node, and each of them has a size 39. That's what we programmed before. The edge indices are always 2. For example, atom Y is connected to atom Z, and there's a whole lot of them, and the edge attributes are always 7 long. And we just printed the first few, so we have a few small string here, and the feature vectors attached to them, our labels, our edge tensors, our edge features. So this is our data set, and it looks good. So we are nearly done. And the only thing that we need to do is program some message passing, and then we are ready to train our very first model that we completely did from scratch, which is pretty cool. So let's go ahead and make a class for our graph convolutional neural network, and we will inherit from, again, PyTorch geometric, a class named NN module. We will also inherit from the message passing class, and I'll talk to you about that in a second. So what do we need to pass? So if we want to make our graph convolutional neural network, we of course need to know how many node features to expect, because that will change the shape of our initial linear layer. If you look at this, we will have a linear layer that is of the size of this, which is the length of the node features plus the length of the bond features. So we need to know how many of them we have so we can set up the stuff correctly. And again, we need to call super. Sorry if you're not into object-oriented programming, to inherit right from that. Now, again, as I already warned you, I will hard code a lot of things. We'll do 3 rounds of message passing. We'll do a hidden size of 300, and we'll use dropout 2%. Of course, these should be hyperparameters and you should optimize them, but for the sake of simplicity in this workshop, we will just hard code them. But don't do this in your own projects if you don't want the reviewers to be mad at you. If you select me as a reviewer and you hard-coded these things, I will complain about them. Okay, so what we'll do first is set up an empty non-trained linear layer, which takes as input, like the input dimension is node features plus edge features, and the output is hidden size. And if you think back to our diagram, this is exactly what this means. We have as input dimension this concatenated atom plus bond, and as output this 300 that we decided for as a hidden size. This is not trained yet, no nothing. We will just define it so that we know that it is there, and we'll call it edge init. You can call it anything you like. But that's the name that I chose for this workshop. Now, what we have to do next is all our convolutions. So we'll have 3 of them. So we'll iterate over self.depth, and then for each of them, we will append to this list of modules a convolutional neural network layer that we will program ourselves in a second. We will call dmpnn-conf, and it only needs to know the hidden size, because if you look at our diagram, this message passing is just of size h times h, so the input is h, the output is h, nothing else. So we only need to pass the hidden size. Once we are done, we want to aggregate the edge to the nodes. This is the 3rd linear layer. So if you think back to the slides, there were 3 of them, and this is the last one, I promise. And the input dimension is our hidden size plus the number of node features. Why? Because this is how we defined it. The number of node features plus the hidden size. And the output will be self.hidden size. We could also decide on something different, but just for the sake of simplicity, we will keep it the same size. That's also how ChemProp, that we will compare to afterwards, works. It will have the same size for atomic and molecular representations. And we will then use a pooling layer, and this is where Alvaro's question comes in. This global add pool just really adds all of our atoms together to get an atomic representation. This is the mean or the plus sign here. You can also have mean aggregation or whatever, a weighted average, whatever you want. We will just sum up everything, so add everything, all the atoms, and this is the global add pool that we imported on the top of this notebook. Now the only thing we need is this neural network, and I'll just very hand-wavingly define a single layer. If you want to do something more elaborate, probably more than one single layer would be needed. You should maybe do 2 or 3, but we will just do 1 to make a small model for the workshop today, and that will be enough. So this is just an initialization. This is just a really like empty list of all the layers that we need. And of course we want to train them. So what we need to define is how we do a forward pass in our model. So given one data point, this is one single molecule with the data that we defined here, so X edge, edge index, edge attributes, Y, and so on. Since I don't want to type data dot something for 100 times, I will just rename all of those. That's not really necessary if you enjoy typing, but if you like to make it fast and save yourself some typing, then you can do this. Now, let's set up the initial edge features. We will get the 2 indices from this edge index tensor, and then we will say our 0th h. So what we're trying to build now is this h0 is you pass in this concatenation of A1 and BY1, and you apply this linear layer to get this H120. So this is exactly what we are going to do here, is H0 is, we will concatenate the respective vector for the atom with the edge attribute. So this is A1, B1, and the dimension of concatenation is 1. If you introduce a few print statements, you will see that this gives you just A1 and B1. So then we want to apply our linear layer that we called edge init. So we'll pass that to edge init, and of course we also need some activation function and not just a linear layer, because otherwise the whole thing will only be linear, and that usually doesn't learn any meaningful thing at all. So we'll pass that through an activation function. You can choose any you like. I'll just use ReLU for this workshop. And this should probably also be a hyperparameter that you pass as argument here. So now that we made our initial H0s, we are ready to do some convolutions. So we do that depth times, so in our case 3 times, and we'll define this update. So the self-confs is this module list of these layers that we defined, and they will take as, so I'll choose the 11th of this, and it will take as input all the edge indices and the hidden representations that we have now. I'll talk about that in a second, but following that chart in our slides, what we want to do is take those, you pass those through a linear layer, and then we add the H0 on top of it. So the convolutions will actually do the linear layer, and we'll program that in a second. So we just need to add H0. And then if you want to use dropout, this is a good place to do so. I will not use any dropout in the feed-forward neural network. That's just because I'm a little lazy today in programming. But of course, you can do anything you like. So we will pass our hidden representations through an activation function again. And then we'll apply dropout with the ratio that we selected, and we'll set this to self.training. This is actually something that we inherited from this NN module. And this is important because we don't want to use dropout during inference. So if you want to predict and we're done with training, we don't want to use dropout anymore. And now we need to do edge to node aggregation. So this is this third step over here. So in our forward pass, we will aggregate and we will let that self-conf layer take care of that. And I'll show you in a second why this makes sense. And we'll again pass the edge indices and all the age that we have now. This will actually not be an additional layer. We will just use the magic behind Torch Geometric to do the aggregation for us, so we don't have to take care of which atom belongs to which molecule. And then we'll concatenate this with the initial features X for each atom, because this is how we set it up in our chart. If you look at this, we wanted to concatenate our A1 with the sum of all the incoming messages. So we'll do that. And then we should also, of course, use an activation function. And we'll pass that through our edge to node linear layer that we had set up in our chart before. And then only the feed-forward neural network is missing. We will use the pooling layer that we defined to pool over the atoms. This will give us molecular embedding, and then we just pass that through our feed-forward neural network. And then we need to take care of our dimensions, squeeze -1, to get the right dimensions that we expect for the prediction. So this is all the magic that we need to do. So this is the whole message passing done. And now we only are missing that DMPNN conf that we used here. And I see that we are running a little bit short on time. So I'll just copy paste from the solutions and go for it, because I really want to have some time for the reactions afterwards. So what the DMPNN conf does is it inherits from message passing. That's again something that we used from PyTorch Geometric, and you can see that the message passing thing, it takes some node and some edge embeddings. It passes that through any function you like, and then you can concatenate, aggregate that in any function you like and add that to your atom embeddings. And this is exactly what we will do now. We will extract our edge indices, and then we will make our messages based only on the edge indices. If you look at how we did our aggregation here, we only have the edge indices here, no atom features. So this is why we'll set X to none. And we'll use the edge attributes that are the current attributes of this. Now, this gives us all the messages from all the incoming atoms. So for example, for that 1 to 2, it will give us 3 to 1, but it will also give us 2 to 1. So the reverse message that we said that we wanted to exclude. So this whole next line is just excluding this reverse message. So we will aggregate our messages and then subtract the reverse message. And we can return our message. This is just the aggregation over all the neighbors. And we use that first thing here when we want to aggregate over all of our nodes. And we use that second part here that goes through that linear layer if we want to do the convolutions in our message passing. So we'll only use that updated edges here. And the message that we are using here is really just the attributes, and all the message passing is in that self.propagate. And I really encourage you to look through the documentation if you want to use it for your own stuff. It's pretty good. And it's pretty convenient that we don't have to worry at all about which nodes and which atoms are connected to which. We'll just see this all here. If we make an empty model, an empty GNN of the dimensions that we used before, 39 and 7, then you see that I have a typo in model.list. Yeah, that's because I gave it a double L. And there's also a typo in d-mpnn-conf. Oh, yeah, this is because this is not a method, but its own class. Sorry about that. And here we have it. Our very first self-programmed graph convolutional neural network. It takes as input our atom and bond features. It turns it into this hidden size of 300. There's 3 rounds of message passing. Then we aggregate that to our atoms and we pass it through a feed-forward layer. And this all takes care of all the heavy lifting. So, which is pretty cool. So now, if we want to train this, we need to load our data set and then train our model. So what we'll need to do next is define a function that trains a model. So it will read from some folder, and of course we need to pass the mode. I'll again do some copy pasting here because that's not super interesting to type. And we want to have time a little bit later for the reaction stuff. So what we'll do, we'll set a seed just to make this reproducible, and we'll load our training set with the construct loader that we already made before, and we'll set shuffle to true because during training we want to shuffle our data points, and for the validation and test set we of course don't want to shuffle the data points, so we'll set shuffle to false. Now, neural networks are very bad at predicting targets that have very different values from 0 to 1. So if you have targets that are 5 million, you don't really want to just pass them to our model as they are, but you want to standardize our targets to something that's between 0 and 1 approximately. So we'll just do that in a very crude way. We will compute the mean and the standard deviation of our training set. That's the only thing, of course, we would know in a real setting, the training set and not the test set and so on. And then we'll define a class standardizer that we'll also program ourselves. And it is really nothing then upon initialization, we assign the mean and standard deviation. And if we call it, we want to take all the data, the targets that we have, subtract the mean and divide by the standard deviation to make them be between 0 and 1. And if you wanted to do the reverse thing, we of course have to multiply the standard deviation and then add the mean to get the target unscaled. So this is just a scalar. And then our model will be the GNN class that we just defined. And we just pass it our num node features and num edge features that we already have in our train loader.dataset object. We will use the Adam optimizer with some learning rate that I thought was good. And we'll use mean squared loss and just sum over all of our data points in our batch. And then when we train, we go through each of the epochs that we want. I just hard-coded this to 30. Again, don't hard-code things in a real research. And we'll call a function train epoch that we'll program in a minute and give it our model, our loader, our optimizer, the loss that we want to use on our standardizer. And then we can do a prediction with a function that we'll also program in a second and then just print our loss. And when we're done with the epochs, we will predict on our test set and just see how that performs. So what we still need is our train epoch and prediction function, and then we are done and we can train our first model. So for the train epoch, we will set our PyTorch model to train. This is very important because that means that we need to track our gradients that we need during the backward pass. We set the overall loss to 0, and then we go through each data in our loader, so through each batch. We set the gradient to 0, and then we pass our data through the model. Which gives us our target predictions. And then we compute the loss based on these predictions, plus whatever we actually wanted to predict. Since it is standardized, we also need to call the standardizer. So this out will be between 0 and 1, but our data.y will be any range that your data is in. So we need to call standardizer on that before we compute the loss. Then we can call backward, compute all the gradients, and have our optimizer make one step and update our parameters to make our loss a little smaller. And of course, we need to add our overall loss, that the current loss that we have in our batch, to the overall loss. So we call the standardizer in reverse mode to get the full range that we want, and we compute the loss to our data, and we add it up because if we return it, then we can just print it to screen. It doesn't really do anything for the optimizer. It is really just about printing to the screen. And for prediction, we pass the same arguments, of course, and we want to set the model to eval, which means that we don't need to track the gradients and we will not do any backward pass. This will make it a little bit faster. Now, we will go through each of the data batches in our loader. We will call the model, get our predictions. We will pass them through the standardizer in reverse mode to get the thing in the right range, not between 0 and 1. And then if you use GPUs for this, which we didn't set up here, then you would need to call detach. Since we don't, we could actually remove this line and just say prets extend pret. But if you ever want this to run on GPU, you will need this, but we were also missing some lines to make this work on GPUs anyways. So with this, we are finally done, and we can train our very first model by just calling train, and we will read from this workshop data set. And let's pray that I typed correctly. The model looks good. And it actually trains. We see some root mean square deviations for training and validations, and they decrease. So it seems to be doing something meaningful, which I'm very happy about. Not too many typos. And you just programmed your very first molecular graph convolutional neural network without any previous input. We'll let this train for a bit and meanwhile talk about reactions. So I already told you that in the end we want to deal with reactions that are atom mapped. So for example, we have these reactants and these products here. We'll print them in a second, and I'll just here make a molecule for the reactants and the products. You see, this is just a dissociated water molecule. We'll again call make mol as before. You'll see the output as soon as my training finishes. It's nearly done. The ESOL dataset is a dataset of solubilities that is truly used in benchmarking for molecular properties. So the timing that you get here is pretty accurate. And really good models in literature are about like 0.6, 0.65, and you see we're not too bad. Although we have a really small model, which is pretty cool. And we're just training on a CPU. If you look at our like RAM and disk usage, it's nearly nothing. And our test MAE is 0.65, which is pretty good. So if we want to standardize, generalize this to reactions, our small string is now reactants and products. We can split this, and have our reactant molecule and our product molecule. And you see, I just detached the first proton in the reactants and then attached it and then detached the second proton. This is also a really good example why you shouldn't just use like the difference in Morgan fingerprints, because the difference in Morgan fingerprints of this will be 0, but clearly there's a reaction happening, namely the H1 attacks at the O and then it bonds to this and the other bond is lost. Now we need to make a CGR out of this, and this is actually very simple, and we don't need to make many changes to our code. We just go ahead to our model graph thingy, we copy paste it, and make our reaction graph. Now, we of course have a reactant smile and product smiles. So we need to split at this larger sign as I did above to get the reactants and the products. And when we make our molecules, we want to make one for the reactants, which is on SMAUS reac, and one on the products, which is of course on SMAUS prot. So we have 2 molecules now, one for the reactants and one for the products. And what I will program now is only valid for balanced reactions. If you also want to do not balanced reactions, you'll have to do a little bit more work, and I'll show you in the end where to copy paste that code if you're interested. So we need to track which atom is which. So we need to make a dictionary of which index of the first molecule corresponds to which index in the second molecule. So we call this reactant index to product index, and we'll make a function for that I'll show you in a second, and we'll just pass the reactants and the products to this function to get this dictionary of which atom is which. And then we'll just count our number of atoms on the reac molecule. It doesn't really make a difference whether you use reac products if your reaction is balanced, because then you have the same number of atoms on each side. So when we set up our feature vector for the atoms, we now have 2 sides for the reactants and the products. Instead of doing F atom, we do F atom reac, and we pass the reactant molecule, and we get the atom with the correct index. And when we do our product feature vectors, we will fetch the right product. And actually there's a little error in the solutions. This should not be A1, but RE2 PI A1, because we need to fetch the right atom in the products. Now you can just concatenate those. In practice, what seemed to work better is if you take the difference, and if your F atom is made of the reactants plus the difference between reactants and products. But again, this is free choice. You can also just concatenate reac and prot and probably get about the same performance that we are getting now. So now we made our double atom vectors. So if you look into our chart, we made this gray part and this red part, and now we need to do the same for the bonds. I just got rid of all of my windows. Here we go. So when we go through all of our bonds, of course, we now need to check whether there is a bond in the reactants and whether there is a bond in the products. Again, for the products, we need to use this dictionary to see which atom is which. And if both of those are none, we'll just skip. And if either of them is not none, we will compute our reactants and our products feature vectors. I'll just copy paste it here. So we'll do our reactants bond features call products bond features call. We'll compute the difference between them, and our f-bond vector will be the reactant part plus difference. Again, you could just do f-bond prot here and probably be equally good. And we are done. This is our condensed graph of reaction. So you see we only made 2 molecules here. We had a little bit extra work setting up the features for the atoms and for the bonds, and we are done. The only function that we are missing is this map reacts to product. This is just some RDKit headache of going through all of your atoms in your product molecule, keeping track which atom number is which index, and then you do the same for the reactants, and then you look up which atom number in the products corresponds to which index, and it gives you your index dictionary. If we do that for the water thing that we did above, then I should probably execute this and not have it as a method in my newly defined class. And then we would see that for this very simple reaction here, atom 1, atom 0 is atom 0 in reactants and products, and so on. Okay, here's a question. How do we automate the generation of a reaction smells? What's a typical reaction equation for you? While you'll type, I'll just show you how a reaction graph looks like. I'm not really sure if I get the question right. Like the typical reaction equation being like reaction smells, or would you do like XML files, or what is a typical one for you? If I pass my reaction smells to this, we see that we now have 4 bonds because we have those directed bonds, and it all looks good. And then we go back to our chemical data set, and the only thing that we need to add, like I'll just copy paste what we had before, and the only thing that we need to add here is that we also have this reaction mode now where we call reaction graph instead of mole graph. Okay, the question that's in the chat, the answer would be if you just have a reaction equation like this, you would need to pass this through an atom mapper. There are lots of atom mappers on the internet, and it will give you the mapped small strings. But we will not cover this today. So we are ready to train our first reaction model, and we'll train it on a dataset of E2 reactions that are also put into into this data folder. It's E2 reactions. If you look at them, it is reactions, and it has barrier heights. This is actually from this ChemProp paper, and we'll reproduce one of those values here for those E2 reactions barrier heights. And what I want to show you here is that the MAEs that other people reproduce are ranging between like nearly 3 to 8 or so. And once our model finishes training, we'll hopefully arrive at 2 point something. So with like really easy coding, you arrive at something that's better than nearly all of the literature. If you think, well, cool, I'm gonna publish this tomorrow and just copy paste, then you're too late because we already submitted this to ChemArchive. But this is how it works. And the really cool thing about this is that you don't need to just train on one reaction type. For example, there's one model that just did like one hot encoding of the different sides of our E2 reaction. Of course, this performs well, but it doesn't generalize at all. But our model generalizes. We can also train this on a very diverse data set of different reaction types without any limits. So this is about what I wanted to show you today for our self-program thing, and I'll use the last like 3 minutes of this workshop to also show you how to use ChemProp. So if you don't want to do all the coding yourself, you can of course use our finished algorithm, and you don't need to use any coding yourself. For this, we need to download the data. It cannot just read from the internet like we did before, and you can run this on command line, which is ChemProp train. We'll specify our training data path. It's a regression task. We want to have a reaction. in and explicit hydrogens. We have this val data path and this test data point, and we also want to see as an axiomatic the mean absolute error, because per default it's only root mean square deviation. And this will train our model without any programming. You will get a little bit better results. You can see here there's an awful lot of arguments that you can pass to this. For example, we'd use 2 layers of feed-forward neural networks in our readout, but you can use anything you like. And if you want to use it in a Python script and not from the command line, the nomenclature you want is import chemprop, pass some arguments, and then call chemprop.train. And that's all in the chemprop documentation if you're interested in that. And if we look into our model training that's still running here, let's see, we are at epoch 12. So still a little time to wait. Also, if we scroll up, and you see we get an MAE of like 3, which is pretty good based that we didn't do any hyperparameter tuning at all. We have a really small model. It trained in like 1 minute on a CPU, on a single CPU. So I think that's pretty convenient. On a real data set, like people really use it for benchmarking. It's not a fake data set that I used for this workshop. It's actually a one that people use for benchmarking reaction models. And chemprop is also nearly done. We are at epoch 25. And we should get a little bit better performance just because the model was a little bit larger. We had a larger neural network for readout. And we also had a little bit better managing of dropout, which was a little bit more consistent. And we see we go to 2.7, which is already better than pretty anything else that's out there. This is chemprop, but if you compare to all the others, we are better than everything else with like 1 hour of coding, which is pretty cool. And that's the end of what I wanted to show you today. And I really hope you enjoyed it and it helped you to program something from scratch without any predefined functions, because I think that's the part where you really get it if you just program it by hand once. Thank you for your attention, and I'm very happy to take questions.
Thank you, Esther. It's not just 1 hour of coding, it's a lot of knowledge, and it was very impressive how simple you presented, but obviously there is a lot of things behind that one should take care when you want to do real science, like, as you say, high parameter optimization, etc. But really, really cool. I really appreciate. I don't know if there are questions here.
So maybe while you type, just something that I wanted to show you, I'll just pull up the solution notebook here. Chemprop has a lot of extra functionality. For example, we could train an ensemble that would just be 1 extra keyword, and we could train an ensemble of, say, 3 models. And then we could use the ensembles that we have to predict and use an uncertainty method based on ensembling. There's also, for example, evidential learning or mean variance estimation that is also inbuilt in chemprop. It's just really like 1 line extra. And then you can, for example, get uncertainties here from the ensemble. So if you plot this, you would get uncertainties with each prediction. You see that this one that is very bad actually gets a really high uncertainty. So that would be cool. And if you plot, for example, the uncertainties that we got here against the true errors, it's pretty well calibrated given that the model is really small. So there's a lot of cool functionality in chemprop that you can use without any coding, just as a heads up if you want to use chemprop.
Okay.
Any questions?
Yeah, I don't see any question. I'm going to stop recording. Thank you so much for presenting today.
You're welcome.